Good afternoon. Thank you very much for being here. I know I'm the only thing between this and reception, so I'll try to be quick. I appreciate your presence. And today I would like to tell you a brief story about topological insulators, especially from the perspective of treating electrons as waves. But before I do that, I want to note that although the ideas I'm about to share are very important to my own PhD work, they're not my ideas. They have been a combination of many years of work by people in the field, and two of them are actually here on the faculty at Penn in the physics department. So let's start talking about topological insulators, but before we do that, before we can appreciate their beauty, let's look more generally at electrical conduction as a whole. Sorry. It probably takes no amount of convincing at all for everyone here to appreciate how critical electronic materials or electricity in general are to our everyday lives. Everything from infrastructure, banking, from government, from education, in fact, relies in some crucial ways on electronic materials to run properly and efficiently. Here I'm just showing a snapshot of the city of Philadelphia at night to illustrate how literally electricity and electronic materials light up our city. So it probably doesn't surprise anyone that it's a very important task to understand states of matter that conduct electricity. So let's start by defining what an electrical conductor is. I'm going to simply define an electrical conductor as a material that conducts electricity. Simple definition, but not very useful, because all it does is restates the two words in the terms. So practically, how do we determine whether something is an electrical conductor? Well, maybe you can imagine doing something like this. You put a mysterious piece of material that you want to know whether it's a conductor or not into a circuit like this with wires, and you put a light bulb into it as well. Then you power up the circuit with some power source like a battery or plugging it into the wall, and if the light bulb lights up, you conclude it's a conductor. If the light bulb does not light up, you conclude it's a non-conductor or an insulator. Well, why does a thing that lights up gives you indication that the material is an electrical conductor? Well, it means that an electrical current was allowed to flow through. You probably all have some sort of mental picture of what a conductor is, probably from high school textbooks or middle school textbooks even. Microscopically, a conductor could be described by a picture that looks like this. You imagine a material with a lot of atoms in there, and each atom has positively charged protons and negative charged electrons, and most of the electrons and protons are bound to each other. Well, but once in a while, some of these electrons hop off, and they can flow around very freely and form an electrical circuit. That's the case in a conductor. In an insulator, that doesn't happen. All of the electrons are somehow bound to a particular nucleus or to the protons, and they can't flow very freely. So you don't have the presence of an electrical current. This simple picture, although naive in a lot of ways, gives us some intuition about what an electrical conductor and an insulator is. But it's missing some crucial ingredients that can't be described by just thinking of the electrons as particles. And this is where we need to borrow some intuition, or rather some insight from quantum mechanics, which says that everything that you can think of as a particle, you can also equivalently think of as a wave. And this is the picture I want us to focus on in the next slide. Now, the protons are relatively heavy, so we can still think of them as particles, and these are illustrated as circles on the plot. But the electrons, by comparison, are much lighter, and they can't be thought of as particles anymore. We have to think of them as waves, which are objects that are extended in space, and that's the wiggles that are occurring on this plot. That's the electron wave. It's not belonging to any particular atom anymore. It's extended throughout the whole crystal. The electronic wavelength, which is the amount of space that you need before the wave starts to repeat itself, is much, much longer than the atomic spacing between any two particular nuclei. And each one of these waves, which a particular wavelength, carries a certain amount of energy. So you can imagine plotting something like this. Energy on this axis and wavelength on that axis. And each one of these dots corresponds to an allowed state of an electron wave with a particular energy and a particular wavelength. What you notice immediately is that there are regions in energy where there are no circles, which means states aren't allowed to populate in those regions. This is what we call a forbidden gap. And the other regions where allowed states are able to fill up are called the electron bands. Using this band picture, we can now explain more precisely what an electric conductor and electric insulator is. Imagine these allowed states. I start filling them in. If I fill them before I meet, and I stop before meeting a forbidden gap, I call that a conductor. Otherwise, I call it an insulator. If I fill all the way up to a forbidden gap, I call that an insulator. And for so long, a lot of people thought that the interesting physics lies in the conducting state because that's the state that responds to an electric field and carries current and carries information. And people thought, well, the insulating state probably isn't as interesting. This is reflected in the way we taught physics for many years. I'm just quoting from a very famous textbook by Ashcroft and Mermet in the field of solid-state physics, and I'm paraphrasing what they said in the first paragraph of the first chapter, is that metals, i.e. conductors, occupy a rather special place in the study because they conduct heat and electricity and therefore provide the starting impetus to the study of modern theory of solids. Well, this idea started to change about 20 years ago when people realized that actually the insulating state is more interesting than previously thought. In the sense that there isn't one particular insulating state, and it's not all the same. There are different insulating states, and for this we need to borrow ideas from topology to explain that. Topology simply, okay, that's not supposed to happen. Topology is a classification where you're classifying things by discrete numbers, things that don't change continuously. And so two things in the same topological class can be deformed continuously from one to the other without doing drastic modifications of the object. So suppose you start with some object, that shape, and you deform it continuously to get this shape. Geometrically, they're very different, from a topological point of view, they're the same. But if you start poking a hole in that, that's a different topological object. So I hope this picture gives you some intuition that topology is really concerned about global properties, not local properties. Locally, these two look different, but globally, they're the same. So if you start applying this idea to the classification of insulators, we're really looking at global objects. We're not looking at a particular electron wave, we're looking at all the electron waves together and how they relate to one another. And if you do that, the band structure that I showed you before, each of these bands you can label by an integer, by a discrete number. For instance, I'm showing you something that has a plus on the bottom and a minus on the bottom, and something that has the opposite. And suppose you take these two materials and you put them together. The only way to go from one side to the other of that type of a material to this type of a material is if something interesting happens in the middle, which is a closing of the gap. Remember, this was forbidden before, but now it's allowed. And that's interesting. And that only occurs at the interface between these two materials. And so topological insulators are insulating in the bulk. They don't conduct electricity in the bulk. But if you put them right next to something which is different topologically, then there has to be some conducting modes that occur at the boundary. So they're insulators in the bulk, but conductors at the boundary. But the conductors at the boundary aren't any ordinary conductors. They're special conductors. They're unidirectional, and they're robust against small perturbations to the system. And this is not just in theory. People have seen this in experiment. Here I'm showing you a plot of experimental data where this is what they're doing. They're trying to image the band structure at the surface, and you see the type of band crossing that I showed you schematically earlier. So what's the central message? The central message here is that not all insulators are the same as previously thought. Depending on how all the electrons waves conspire together to give you a topological classification, you can have insulators that are distinguished by discrete integers. These topological insulators are insulators in the bulk, but they're conducting on the edge. They have robust conducting modes that are insensitive to small perturbations like disorder, temperature fluctuations, etc. And their robustness makes them appealing for making electronic applications with low heat loss for designing a possible quantum computer, which is a long time from now, but it's a dream of physicists, and for other future applications yet to be conceived. Thank you.